In an experimental aerothermodynamics class, a team of 5 students collaborated and conducted an experiment on a cylinder that was placed in the test section of Cal Poly's low-speed wind tunnel. The team analyzed different flow regimes with various Reynolds numbers. The objective of the lab was to determine the pressure drag coefficient, evaluate the effects of Reynolds number and surface roughness, identify sources of uncertainty and error, and place a qualitative and quantitative value to flow visualization captured by the team.
The following variables were used by the team in various equations.
Many important concepts were used to develop the background of this experiment, including Reynolds number. The Reynolds number expresses the ratio of inertial forces to viscous forces. For airflow past a circular cylinder, the drag of moderate or high Reynolds numbers is primarily the pressure drag. As an object moves through the gas molecules stick to the surface. This creates a layer of air near the surface called a boundary layer, which in effect changes the shape of the object. Boundary layers may be either laminar or turbulent depending on the value of the Reynolds number. For lower Reynolds number, the boundary layer is laminar and the streamwise velocity changes uniformly. For higher Reynolds numbers, the boundary layer is turbulent and the streamwise velocity is characterized by unsteady swirling flows inside the boundary layer.
Boundary layer separation occurs when the boundary layer may lift off or separate from the body and create an effective shape much different from the physical shape. This happens because the flow in the boundary layer has a very low energy relative to the free stream and is more easily driven by changes in pressure. In the experiment, the team created a boundary layer trip by attaching a trip strip to the cylinder that would introduce instability into the boundary layer.
Flow past a cylinder varies based on wind tunnel conditions and the velocity of the free stream. As velocity increases, Reynolds number increases as well. With regards to tripping the boundary layer, drag depends on the flow in the boundary layer. It is observed experimentally that a roughened cylinder or ball will transition to turbulent flow at a lower Reynolds number compared to a smooth cylinder or ball.
It was expected that a high Reynolds number would result in lower coefficient of drag due to reduced separation. With the addition of the trip strip, the coefficient of drag would be further reduced from the more turbulent boundary layer.
At the lower setting of 200 RPM, the team predicted that there would be an oscillating Kármán wake, as the Reynolds number of the flow at 200 RPM is 5 times 10 to the 4th, which is easily within the span between 300 and 3 times 10 to the 5th at which this occurs. At the maximum setting of 600 RPM, the team was unsure as to what flow behavior would be present. The Reynolds number at this setting is roughly 2 times 10 to the 5th, slightly less than the Reynolds number of 3 times 10 to the 5th, at which the wake transitions from a Kármán vortex wake to the narrow wake caused by the boundary layer becoming turbulent.
The team used Cal Poly's low-speed wind tunnel as the overall apparatus for this experiment. A smooth surface cylinder was mounted across the test section. A total of 24 evenly spaced static ports exist on its surface, about every 15 degrees around the circumference. This was used to measure the pressure distribution around the cylinder. First, the team reviewed the safe working procedure for the wind tunnel and noted the conditions in the lab. Then they measured and recorded the cylinder's dimensions and position in the tunnel. Throughout the experiment, the team took pictures of the pressure taps and noted any sources of potential error they observed. The team verified with the TA which transducer ports were static taps. Before turning the wind tunnel on, the team recorded wind-off data and atmospheric conditions. Before starting up the wind tunnel, the team ran a final safety check. Each team member was in charge of operating either the smoke, laser, lights, or videos. The smoke machine shown in this video produced smoke that was circulated through the tunnel. The laser and floodlights shined down onto the cylinder. The combination of the smoke and lasers provided flow visualization. Throughout testing, a team member checked the cylinders and taped items to ensure everything was secure. During the experiment, the team ran the tunnel at 200 and 600 RPMs with and without a test strip on the cylinder. When the team ran the wind tunnel at 200 RPMs with the smooth surface cylinder, they recorded 100 data points at each of the 24 ports. The team did this data recording method 3 times. Then they turned the tunnel up to 600 RPMs and repeated data collection. Next, the team turned off the tunnel and attached the boundary layer trip and repeated the experiment. The trip strip was 1.5875 millimeter diameter rubber wire. The team taped it along the length of the cylinder at 82 and 278 degrees with 0 degrees starting at port 12 going clockwise.
The video shot at 200 RPM validates the team's prediction of an oscillating Kármán vortex wake with large vortices easily visible in its smoke. At 600 RPM, the wake behaves significantly different, with no large vortices and a thinner wake. This led us to conclude that the boundary layer had undergone turbulent transition.
To calculate the drag, the surface of the cylinder was approximated with panels tangent to each pressure port. The pressure measured times the length of each panel is the force on the local surface. The sum of these in the direction of the drag is the two-dimensional drag, or drag per unit length. However, there is some error associated with this due to the fact that the panels do not follow the surface exactly, and it does not capture friction drag at all. The following plots were generated using the data the team collected in the wind tunnel. This plot shows the three-dimensional pressure profile on a cylinder as it allows for better visual interpretation of the data. It is easy to see that, as was previously mentioned, that at the stagnation point there is a coefficient of pressure of 1, and it can be seen that pressure decreases as the flow moves towards the back of the cylinder and stays relatively constant across the back. It is also clear that there is symmetry over the horizontal axis going through the cylinder, but not over the vertical axis. As was mentioned previously, in an ideal case, the invested flow over a cylinder would not separate, and the streamlines would be symmetric across both the vertical and horizontal axes going through the cylinder, meaning the pressure distribution over the cylinder would also be symmetric about both axes. The plot shows the coefficient of pressure result for the flow characterized by a Reynolds number of 5.81 times 10 to the fourth, which is considered to be laminar. It can be seen that the flow separates somewhere at about 70 degrees from the leading edge. In this area behind the point of separation, there is a wake, which results in low pressure across the back of the cylinder. The separation therefore results in the asymmetry that is seen in the pressure distribution across the vertical axis of the cylinder. The pressure coefficient of the trailing edge for the cylinder without the trip strip was approximately negative 1.5 and was approximately negative 1.7 for the cylinder with the trip strip. Typically, a trip strip is added to induce a turbulent boundary layer, which results in delayed flow separation. If that had been the case, the pressure on the back of the cylinder would have been higher with the trip strip versus without the trip strip. However, because this experiment was conducted with the trip strip placed past the point of separation, it actually resulted in a larger wake, which therefore resulted in the pressure on the backside of the cylinder being lower with the trip strip than without it. When the wind tunnel was run at a higher Reynolds number of 1.96 times 10 to the fifth, the results showed a similar trend to the test at a lower Reynolds number, where the trip strip resulted in a larger wake, resulting in lower pressure on the backside of the cylinder than it did without the trip strip. At this Reynolds number, it can be seen that the trip strip had a greater effect, as there is bigger difference between the coefficient of pressure on the backside of the cylinder between the two cases. With the trip strip, the coefficient of pressure was approximately negative 1.5, and without the trip strip, the coefficient of pressure was approximately negative 1.2. This is most likely because the trip strip was closer to the point of separation, since at a higher speed the flow will separate further back. If the pressure distribution for the low Reynolds number is compared to the pressure distribution for the high Reynolds number, it can be seen that for the case with the trip strip, the high Reynolds number gives a coefficient of pressure of approximately negative 1.2, which is greater than the coefficient of pressure for the low Reynolds number, which is approximately negative 1.5. This is because at high Reynolds numbers, the flow becomes less laminar, which allows it to stay a touch longer, resulting in less of a pressure gradient. The pressure distribution on a surface can say a lot about its aerodynamic performance. The area between the two curves is the two-dimensional lift coefficient. The y-axis is inverted so that for the airfoil, the upper surface with a lower pressure will also be the upper curve. This is not true for the cylinder measured, which indicates a small downward force on the cylinder caused by the vortices in the wake causing downwash on the cylinder itself. These can be compared to the invested case where there is no lift generated due to the symmetry of the streamlines.
To calculate drag, the panel method was used as it is the most accurate method available. A significant feature of this plot is that the coefficient of drag of the cylinder is larger with the tripwire compared to the coefficient of drag without it, and the error bars show that this isn't a statistical aberration. This is due to the placement of the tripwire after the natural boundary layer separation point, and thus it only served to block the flow of the air around the cylinder and therefore increase drag. Perhaps if the boundary layer had been tripped sooner along the surface of the cylinder with the tripwire, the turbulent boundary layer's mixing action hypothetically re-energize the air behind the cylinder and thus reduce drag to some degree, but the data displayed in this graph suggests that this did not happen in the experiment due to the placement. Evident in this published plot of the coefficient of drag for a cylinder versus Reynolds number, which has been annotated, is the fact that the measured coefficient of drag is significantly smaller than the published coefficient of drag for the same Reynolds number. While the team only measured pressure drag and not friction drag, the team operated at Reynolds numbers larger than 10 to the third, above which the friction drag is negligible. See citation 7. The decrease in the coefficient of drag as Reynolds number increases in the regime of 5 times 10 to the fourth to 2 times 10 to the fifth was found in the measurements and is mirrored in the published plot. This supports the hypothesis that a more turbulent boundary layer has more near-wall momentum and replenishes this momentum faster due to the turbulent mixing action, allowing the turbulent boundary layer to exist longer in an adverse pressure gradient, which exists at the shoulder of the cylinder, and thus creating less drag.
While the team tried to decrease error and uncertainty by following a detailed experiment plan, error was seen throughout the graphs and are indicated by error bars in the plots. One source of error was the tape that secured the trip strip. The tape is not as smooth as the cylinder and has a small height. This affects the coefficient of drag, thus affecting the boundary layer. It disrupts the flow, similar to the tripwire. A potential source of error also is the calibration of the pressure ports. While the team verified that they were zeroed correctly by taking data without the wind tunnel running, a measured increase or decrease in pressure might not be exactly equal to the actual increase or decrease in pressure. Also, at low velocities, the pressure reports do not read as accurately as they do at higher velocities. The standard deviation is fairly low at high velocities and large at low velocities. Also, doors opening while collecting data had low influence, but they did affect the circulation of flow. It created a gradient in the flux field at the inlet of the wind tunnel. Lastly, the boundary layer due to the wall affected flow visualization.
In conclusion, the data showed that higher Reynolds number did have a lower coefficient of drag, but contrary to expectations, the trip strip increased the coefficient of drag. In addition to this, there was a significant difference between the measurements and what was predicted by potential flow theory, due to the strong influence of viscous effects causing vortices and separation. One example of this is the down force on the cylinder caused by asymmetric streamlines. Flow visualization, qualitative and quantitative analysis is useful in the design of systems which depend on aerodynamic performance. Even simple shapes like cylinders are found in pylons, struts, and landing gear, and they can have a big influence on performance.
The drag on a sphere is generated by the boundary layer separated from the back. As the flow separates, it creates a viscous wake behind the ball. A large wide wake generates a large amount of drag. A thin wake produces less drag. The thickness of the wake and the drag on the ball depends on the conditions in the boundary layer, which depends on the Reynolds number. As shown in the plot, the drag coefficient has a high value at a low Reynolds number, then drops down to a lower value from which it continues to increase with increasing Reynolds numbers. At a lower Reynolds number, the boundary layer is laminar and the wake is thin. As Reynolds number increases, the boundary layer transitions to turbulent, which produces a thinner wake. As speed and Reynolds number increase, the wake thickens and the drag increases.
The following equations were used to analyze the data collected by the team. The following references were used to assist the team to gain further knowledge and information for the experiment.